Okay, greetings. Welcome to today's class. So we were looking at the Otto cycle yesterday. So just a quick recap. We were looking at what are called as air standard cycles, which are typically used to do a first cut analysis of IC engine performance. And we saw what was an air standard cycle, what were the assumptions typically made, and we started off with the Otto cycle, right? And just to quickly recap what we discussed, looking at the PV diagram of this Otto cycle. So we mapped the various processes of intake, compression, power stroke and the exhaust stroke, which are typically found in a 4-stroke IC engine. And we observed that it was mapped to a simpler version, where the so-called pumping losses were not considered. So as far as the Otto cycle is concerned, we consider an equivalent piston and cylinder assembly in which the working fluid is just air, and we start from the compression process. Okay, we do not consider the intake and the exhaust processes as such. We only consider the compression process, which will be 1 to 2. Then the combustion process is replaced by a heat addition process that takes place at constant volume. Then there is an expansion process from 3 to 4, which is once again assumed to be isentropic, and 4 to 1 is a constant volume heat rejection process. And the motivation for this approximation comes from the shape of the PV diagram, which is typically observed when we do measurements from a gasoline or a petrol engine. Okay, so that's the motivation here. So just to list all the strokes, all the processes in an Otto cycle, or I should say in the Otto cycle. The process from 1 to 2 is isentropic compression. Okay. The process from 2 to 3 is constant volume heat addition. The process from 3 to 4 is isentropic expansion. The process from 4 to 1 is constant volume heat rejection. So these are the 4 processes, right, that are involved in this air standard Otto cycle. So some people will call this as the air standard Otto cycle, some could refer to as just the Otto cycle and so on, right. Okay. So now if we were to draw the TS diagram for the same cycle, okay, we will shortly see that sometimes the TS diagram is also pretty useful in analyzing these processes. T stands for temperature, S stands for entropy. Okay. So if we were to map the same 4 processes, let us say we start with state 1, 1 to 2 will be isentropic compression. So in the TS plot, it is going to go vertically upwards, right. So that is going to be isentropic compression, and 2 to 3 is constant volume heat addition. So it is going to go something like this. 3 to 4 is isentropic expansion. So that is going to go something like this, and then 4 to 1 is constant volume heat rejection. Okay. So if I were to mark all the processes, it is important to mark important characteristics of each process and also the direction of the entire cycle, right. So this will be V equals constant, V equals constant. Okay. So those are this is the process where heat is added, and this is the process where heat is released. Okay. So, these are the 4 processes of the same air standard Otto cycle expressed in the TS plane. Okay. So, now if I were to obtain an expression for the thermal efficiency of the air standard Otto cycle, you can immediately see that the thermal efficiency for the air standard Otto cycle is going to be the net work done divided by the net heat which is input, right. So, efficiency is like output by input. In this case, the output is the net work output of the Otto cycle, the input is the heat input which we given, right. So, how do we get expressions for these, right. So, recall that the first law of thermodynamics can be expressed as in differential form, right. So, it can be expressed as delta Q minus delta W equals dE, where the net energy E is the sum of the internal energy plus the kinetic energy plus the potential energy, right. So, this is a standard form for the first law of thermodynamics that people will use. Okay. When integrated over a cycle, what is going to happen? You are going to get delta Q minus delta W equals integral over the cycle dE, right. So, kindly recall from thermodynamics that heat transfer and work interactions are all path dependent quantities, right, whereas the net energy is a path independent quantity, right. So, if I integrate over a cycle, what is going to happen to this integral over a cycle of dE? This is going to become 0, right, because we end up at the same initial state, right. So, essentially since it is a path independent quantity, it only depends on the final state and the initial state, and since the 2 states happen to be the same, the net change is going to be 0. So, the net heat transfer is going to be equal to the net work output for a cycle. Okay. This expression is true when you have a cycle, right. So, the net heat transfer over a cycle is going to be equal to the net work output from that cycle. So, what can we say about this Otto cycle? The net work output of the Otto cycle should be equal to the net heat input given to the Otto cycle. The net heat input is going to be the heat which is given in minus the heat which is taken out or rejected, right. That is going to be Q in minus Q out. So, going back, this would give me eta thermal for the Otto cycle will be equal to W net by Q in, that is going to be equal to Q in minus Q out divided by Q in, which I can rewrite as 1 minus Q out by Q in, okay, very standard expression. So, now what about the expressions for Q out and Q in, right. So, that is the next analysis that we need to do. So, if you recall, the heat addition takes place at constant volume, right. So, the heat addition process is the process from 2 to 3, right, that is the one which takes place at constant volume, right. So, if we integrate the first law of thermodynamics over the process 2 to 3, what are we going to get? So, this is going to be Q in, this is going to be equal to 0 because the heat addition process takes place at constant volume, okay. Then this I can write it as U3 minus U2 neglecting changes in kinetic energy and potential energy, which is a reasonable assumption here, right. So, considering the system and the process that it undergoes, I can neglect the changes in kinetic and potential energy. So, this implies that my heat input Qin is going to be equal to U3 minus U2, right. So, that is one. Similarly, I can consider the heat rejection process, that is from 4 to 1. So, doing the same analysis from 4 to 1, okay, dq 4 to 1 delta W, 4 to 1 dE, we are going to get Q out to be equal to U1 minus U4. Of course, here like the if I have to be very careful, I should have written this as the absolute value of Q out, okay, going back, right. So, because Q out is a heat rejected from the Otto cycle, right. So, the sign convention in thermodynamics is that like if heat is taken from the system, its sign is negative, okay, and if heat is given to a system, the sign of that quantity is going to be positive, okay. So, that is the sign convention that we utilize, right. So, I will use the Q out instead of that, I will use the absolute magnitude of Q out, okay, here, even here, okay. So, you can immediately see that this Q out is going to be negative because U1 is going to be less than U4. So, this implies the absolute value of Q out is going to be equal to U4 minus U1, okay. So, I am just rewriting so that we are consistent, okay. So, now we are all set to look at the thermal efficiency expression once again. So, we can immediately see that the thermal efficiency of the air standard Otto cycle is 1 minus magnitude of Q out by Qin. This is going to be 1 minus U4 minus U1 divided by U3 minus U2. And assuming constant specific heats, we know from thermodynamics that delta U is going to be Cv times delta T, right. So, we make the assumption of constant specific heats. So, this is going to be 1 minus Cv T4 minus T1 divided by Cv T3 minus T2. So, Cv and Cv cancel off, okay. So, we are not yet done, right, we need to simplify it further. Now, what we have done, we have essentially reduced the expression for the thermal efficiency of the Otto cycle in terms of temperatures at the critical states, right, the 4 corner states, if I can call them that, right, or the nodes are 1, 2, 3 and 4, right. So, we have reduced the expression in terms of temperatures. Now, let us go further, right, let us use the other 2 processes, right. So, till now we have used processes 2 to 3 and 4 to 1. What about the other 2 processes, right? So, let us look at the isentropic compression process. Isentropic compression process is the process from 1 to 2. So, the process relationship is going to be typically the isentropic process is basically governed by PV power gamma equals constant. That is how we define write down what is called as the process relationship, right, for an isentropic process. So, using the ideal gas equation of state along with that, we can always rewrite that as TV power gamma minus 1 equals constant. So, I can write T1 V1 power gamma minus 1 equals T2 V2 power gamma minus 1. Okay. So, this is what is called as a process relationship. Okay. So, this governs the isentropic process. So, this will give me T2 equals T1 V1 by V2 to the power gamma minus 1. So, by the way, what is gamma? Gamma is nothing but the ratio of specific heats Cp by Cv, right. So, typically its value is taken as 1.4 for air under standard conditions, right. So, that is the meaning of gamma. So, now if we look at this, T2 is T1 V1 T1 times V1 by V2 whole power gamma minus 1. But what is V1 by V2? If we go up, V1 is the volume at bottom dead center, V2 is the volume at top dead center. So, what is the ratio called as? Compression ratio, right. So, that is the definition of compression ratio. So, immediately we can see that T2 is going to be equal to T1 R to the power gamma minus 1, where R is nothing but V1 by V2. Okay. So, this is the compression ratio R. Okay. So, similarly, let us consider the isentropic expansion process. Which is from 3 to 4. So, what happens here? So, the process relationship becomes this. So, this will give me T4, or I can say T3 equals T4 V4 by V3 to the power gamma minus 1. So, once again, what is V4 by V3? V4 is here volume at VDC, V3 is also volume at TDC, right, because the heat addition and rejection process both take place at constant volume. So, what is going to be V4 by V3? Once again R, the compression ratio, right. So, this implies that T3 is going to be equal to T4 R to the power gamma minus 1. Okay. We are almost done now. So, substituting these, we immediately get the thermal efficiency of the air standard Otto cycle to be 1 minus T4 minus T1 divided by, for T3 I am going to substitute T4 R to the power gamma minus 1. For T2 let us substitute T1 R to the power gamma minus 1. So, if you simplify this, what is it that we will get? We can immediately see that R to the power gamma minus 1 is common in the denominator. If you take it out, you get T4 minus T1, and that factor cancels between the numerator and the denominator. So, the thermal efficiency of the air standard Otto cycle reduces to 1 minus 1 divided by R to the power gamma minus 1. So, you see that it reduces to a very simple expression. Okay. So, the thermal efficiency of the Otto cycle depends only on the air standard Otto cycle, right, depends only on the compression ratio R. So, we can immediately observe that as the compression ratio increases, the value of the thermal efficiency also increases, right, because you can immediately see that as R increases, R power gamma minus 1 will increase, its reciprocal will decrease, and we are subtracting a smaller number from 1, right. So, the thermal efficiency will increase, right. But however, we will later study what is called as the phenomena of knocking in SI engines, and this limits the value of R. Okay. So, we can keep on increasing the value of compression ratio. Okay. There is something called knocking in SI engines, which restricts the value of R. Okay, we'll look at that later. Okay, when we come to the analysis of the combustion process in SI engines. Okay, so to quickly summarize, in the air standard Otto cycle, we looked at the 4 processes. The main feature is that like the heat addition process is assumed to take place at constant volume in the Otto cycle. We use simple expressions that we learnt in thermodynamics, right, to derive an expression for the thermal efficiency. Okay, so that is what we have done. Okay.